So I'm here with, this is Paul Verschure with Kathleen Rockland at the Kathleen Center for Theoretical Physics. We're both attending a workshop on network architecture and the brain. And Kathy, you gave us a presentation yesterday where you really gave us quite a broad overview of the anatomy of mainly cerebral cortex.
Yes.
So what do you think are sort of the key properties of a neocortex that we should be aware of?
Of the neocortex. Well, let me start with what may seem backwards and say I think the distributed property, most people are not going to say this first thing, but if you look at these axons and you look at the divergence and you look at the collateralization, the first word, English word that comes to your mind is distributed or divergent. Now we can proceed a little bit more. That immediately gets you into questions of probably random or specific, which we can come back to. I'm not saying random. I'm just saying simple fact of distributed. And so that's one thing we can come back to. Probably what most people would then talk about the cortex is because it's been promoted, a uniform organization. This is what we were talking about at lunch. But that really, if you look closely at the anatomy, that's not the first thing that comes to mind. I could show you pictures later, or we can develop that theme also. Having said that, I would then introduce the idea that, which many people are saying, that the anatomy and the function is a little bit discrepant. So we've been, again, trained to say structure-function correlation. But now it's very clear that there can be functional aspects and structural aspects, and sometimes there's an apparent discrepancy. Cortex, of course, can deal with it, but for us, it looks...
Can you give an example of this discrepancy?
Yeah, I think, and we might have talked about this yesterday also. One of my favorite examples, and you can pick this apart, please, is ocular dominance columns in the monkey. So you are shown ocular dominance columns with beautiful 2DG. So an eye is blocked, and you see the 2DG pattern more or less through the layers. It's very convincing. It's very real. Then you are told what is truth, that more or less, that the basis of this is thalamocortical connectivity. Now, there are actually several things to say about that. One is, if you look at the scale of the anatomy and the functional column, there's an immediate mismatch. So in layer 4C, the main layer, parvocellular axons are smaller than 500. I should say the ocular functional columns are about 500 microns in diameter. But the parvocellular LGN is smaller, 250. Magnocellular is larger, two or three clusters. Then 4A, you have another population of thalamocortical axons. It's very small, 100 microns center to center. Sometimes they're collaterals in layer 6. These tend to be smaller. The cytochrome oxidase population is the axons are equal or less than 100 microns. And in layer 1, whatever goes up there from the LGN is very divergent. So I was puzzled by this for a long time, and my own explanation is there must be some operation, some operation, which is making those axons converge. And the key word here would be maybe something operation, and converge in a 500 micron space. And the two candidates would be something molecular, going back to development, presumably, maybe extracellular matrix, and activity related, or both. Okay, so here, let me summarize. The functional column is unambiguously 500 microns, but the anatomical basis of this, the primary anatomical basis, is all, I'll use the same term probably several times, all around the block. Now, of course, the reconciliation, we think, would be from the intrinsic processing, but that gets you it's not the same thing as saying thalamocortical connections are the basis of ocular dominance cones. It means that the intrinsic cortex is doing something on those connections.
But how do you then define this functional scale of organization of 500 micron?
What you would see, so my first response is operationally that you can link, if you have a functional marker like 2-deoxyglucose or CFOS, and you can link it to a behavior, you will tend to see often a columnar organization of this amount. Does I want to go a little bit further?
No, go ahead.
But having said that, there is some beautiful work, and I'm sorry I forget the authors here, but it was within the last 5 years on the CFOS of might have been Japanese group, Yamamori, where they were looking at different conditions of ocular deprivation in the monkey in CFOS, which is a better resolution than the 2DG. And they would see, they were able to see several laminar patterns depending on the time interval and what they had actually done with the ocular dominance. So even there is a suggestion that when you're looking at average techniques, it's telling you part of reality, but not the whole.
Okay, so one bottom line of this is that structural and functional organization does not necessarily match.
Not
right?
to the investigative view.
Right.
So it works in biology, but not in the way we might think.
Right. So there's no simple mapping between the two.
Often not. In fact, when it occurs, it's almost the exception. And one exception would be, for example, cortical spinal tract, where you have the difference of primate with the fine pincer movement versus the carnivores that cup, and there is an anatomical basis, or even the development of the cortical spinal tract. So babies can't walk until the cortical spinal tract does something, myelination, maybe other things. But I've come to think it's almost the exception rather than the rule.
Okay. But now in your presentation, you also went a bit further than that, right? Because you also pointed out that the sort of standard notions of feed forward and feed back that people have been using to describe the structure of the cortex might not be that clear-cut either.
Absolutely. And I think in several ways. One, even if you take the schematic, the strong view with layers and so on, there are many exceptions, really abundant exceptions. And when you go to the rodent, it's been well known for years that the laminar-based scheme breaks down in a big way. You have a Layer 1 is favored maybe by what could be feedback. Layer 4 is favored, but there's a tremendous blurring. So, but even within primate, you have a lot of exceptions.
But what are the rules really on which we have these exceptions? So
what do you mean by?
Well, if you say you have many exceptions in rodent and also in monkey, but then there's a rule to which you have an exception, right? So, so what's the rule for it?
All right. Well, the old rule, which has some basis in fact, in static anatomical fact, is that, feed forward. See, it's really based on a relay view of the brain, and I don't think that's very useful. But if you accept that relay view, the visual information goes to the eye, goes to the LGN, goes to V1, and so on. Then, and of course, V1 goes to LGN, but also other things go to LGN. So none of these are pairwise. Absolutely none. When you get to V1 and you say, okay, let's start the relay from there. And if you do V1, V2, let's just put in MT, extrastriate, V4, infratemporal cortex, there is, you can plausibly say layer 3 goes to layer 4, input layer in your feed forward. And the feedback is actually usually 2 layers, layer 6 and layer 2, feeding back to layer 1 and sometimes layer 6. But there is a dissociation. One can present a dissociation of a layer 4 based feed forward and a layer 1 based feedback. And there also is, these were the data I was showing yesterday, a dissociation in spatial organization. Feed forward tends to have smaller arbors, sometimes multiple. Feedback divergent in layer 1. But I would still, I suggested yesterday and would still like to suggest that you can rephrase this in terms of a layer 1 organization or a layer 1 biased connection and a layer 4 biased connection. There's no real need to say feed forward and feed back in that. And it has a very bad assumption of saying, well, something happened and then there was a feedback. But we don't know when the film started. So there is a strong assumption in the terminology of this temporal or relay pattern, which I think is not, it can be useful to an extent, but it cannot be the whole truth.
Mm-hmm. Right.
So that's
okay. But then another issue then becomes this so-called uniformity of cortex, right? So for instance, you would say, well, we have a layered structure, and cytoarchitectonically, it sort of roughly remains the same if we sort of go from the front to the back, right? And also there would then be this idea that maybe in terms of their functional organization, things will change in the sort of occipital areas and parietals, more sensory, and if you go more frontal, it becomes more motor. Is that then at least a pattern we can still sort of adhere to?
Yes, by all means. But of course I'm going to say but. And you have to keep in mind the threshold problem, so which is glaringly obvious in fMRI. So if you set if I understand correctly, if you set your threshold low enough, you're going to see lots of stuff. And it's apparent, I think, well, V1, your sensory areas in the adult, in the primate, probably do function strongly unimodal. But there are these cross-modal connections. Even in monkey, I'm going to say it's in the peripheral visual field. Maybe a little bit less in the fovea. So this again would substantiate the threshold phenomenon. But in monkey V2, to some extent V1, you have, in V2 it's quite respectable. You have auditory input, you have some sensory input. In the rodent, you have